Here are a few examples on solving quadratic equations by completing the square. Now, while quadratic equations can be solved with other methods, these examples are going to show you the specific process of completing the square. For example, this quadratic of g squared equals 2g plus 24. If we set that equal to 0, g squared minus 2g minus 24 equal to 0, it will actually factor very nicely into g minus 6 and g plus 4, in which in factored form we can set each of those factors equal to 0, and g ends up being 6 and g ends up being negative 4. So after we complete the square, that's what we should get. Also, if you were to graph it, those are going to be the zeros. Graphically, these are the zeros, which are also called the x-intercept. Okay, so completing the square. Still have to get all the terms on the same side, so I'll subtract the 2g and subtract the 24, set it equal to 0. All right, so the first step was to make sure that the g squared term coefficient was 1, so we're good with that. The next thing was to group the first two. So group the g squared minus the 2g, leave this space, do the subtract 24, and then come up with that magic number, if you like, where you took half of the negative 2, which is negative 1, and squared it, which is positive 1. So you add 1 inside the parentheses and subtract 1 outside. And then whenever you factor that trinomial that you have grouped together, this guy, it will always factor into being x, and then whatever that number was whenever you halved the middle term, half that b value. So in this case, it's the half of the negative 2, which was negative 1. So when we factor that, it will factor into exactly g minus 1, g minus 1. Like there's no, you don't even have to think about it, because that will match the half of the b term that you did before. And then you can write that as g minus 1 quantity squared. And then you have to clean up where you subtracted what you added from the inside, keeping in mind any negative signs that are there. Those do attach, so negative 24 minus 1 is negative 25 equals 0. And now we'll solve for g. This is in vertex form. If you notice from before, vertex being 1 and negative 25. But we're solving here, not getting the vertex. So I want to get the g by itself, which is going to involve a plus or minus of a square root. But I have to get this chunk that's squared by itself. So I'll add over the 25. And I'll get g minus 1 squared equals positive 25. Then I will plus and minus the square root. And you get g minus 1 equals plus or minus 5, since 25 perfectly square rooted. And then you'll add the 1 over. And that'll look like 1 plus or minus 5. So your two answers are 1 plus 5, which is 6, and 1 minus 5, which is negative 4. And those are your solutions, or your zeros, if you like, of the quadratic equation found using the process of completing the square. But again, please note that they are the exact same answers that we got from factoring, which they should be. And they should be the same as from a graphical representation of this quadratic if you solve it equal to 0 and type it in the calculator correctly. This other example will involve a few more steps, only because the squared coefficient is not 1. So if I divide and factor out a 2 from everything on this example, 2r squared plus 4r minus 5, I get 2 times r squared plus 2r minus 5 halves. And then the 2, I'll group the r squared and the 2r, leave a space. Got this subtraction of the 5 halves. I'm going to leave another space so I can add my magic number. So I'll do half of 2, which is 1, 1 squared is 1, so I'll add 1 inside, subtract 1 outside. Again, when you go to factor, the r plus or the r minus that same quantity, you end up getting, whatever you did to half it, that's what it factors to. So the r squared, that trinomial, r squared plus 2r plus 1 will factor into r plus 1, r plus 1. I mean, again, that's the whole purpose of completing the square is whenever you take half of that middle term and square it, the step here, that is what goes in the factored form, whether there's fractions, whether there's whole numbers, integers, whichever, that is what it factors into, is that variable plus half of that r term and that whole quantity squared. Bringing down the other things, there's a 2 out front, cleaning up the negative 5 halves minus 1. Negative 5 halves minus 1 is like negative 5 halves minus 2 halves with a common denominator, so you get negative 7 over 2. Redistributing the 2 through, you get 2 times the quantity of r plus 1 squared, and then just subtract 7, because if you do 2 times negative 7 over 2, 2's cancel. And now we'll solve for r, much like we did in the last example. We have to get that piece, that chunk that's squared alone, so we can plus or minus square root both sides. So I'll add the 7 first, and I'll get 2 times r plus 1 squared equals positive 7. Then I'll divide both sides by 2 and get r plus 1 squared equals 7 halves. Then you go and you plus or minus square root on each of those. Let's see. Divide square root. Yeah. So you get r plus 1 equals plus or minus the square root of 7 over 2. And then whenever you subtract 1, you get negative 1 plus or minus the square root of 7 over 2. Now, I'm not really sure what you would be expected. Obviously, you can get decimal representations for this, but the square root of 7 over 2 as an entire fraction, if you split that, the square root of 7 over square root of 2, and then you go through and you rationalize the denominator, which is the process where it gets the radical out of the bottom. You do square root of 2 to the top and the bottom, and that becomes square root of 7 square root of 2 over 2. So that's the square root of 14 over 2. Again, that's an algebra skill that's learned along the way. So what you get for your solutions are negative 1 plus or minus the square root of 14 over 2. Numerically, though, you get the same thing. But those are your two solutions. Negative 1 plus the square root of 14 over 2, and negative 1 minus the square root of 14 over 2. The third example are not so nice fractions. You still have to get the terms on the same side of the equation. So we'll subtract over the 1. So we get 5p squared plus 9p minus 1 equals 0. The 5 that's on the p squared needs to be factored out. And this is not a nice one because none of the other terms nicely divide by 5, but I wanted to show the example just for process. So if I pull that 5 out, which again is essentially like dividing everything by 5 to factor it out, you're left with p squared plus 9 over 5p minus 1 over 5 equals 0. Then we'll group the first two together. We'll put the p squared plus 9/5 p, leave a space, minus 1/5, leave another space, and then we'll find that magic number, which is half of 9/5 squared, and that's 9/10 squared, which is 81 over 100. So we add 81 over 100, and we subtract 81 over 100, and then we get to play cleanup. Now this is the point where students get to, they're like, I don't know how to factor with a fraction, but you do, because you've kind of already found it's going to be p, and and they'll be the same thing, and that same thing is what you got when you first halved that 9 over 5. So it'll be p plus 9/10, p plus 9/10. It will FOIL back out to give you that trinomial from above. And that's written as p plus 9/10 quantity squared. The 5 still comes down. If you clean up, get a common denominator for negative 1/5 minus 81 over 100. The common denominator is 100. Times this by 25. No, not 25. Times this by 20, times the top by 20. You end up with negative 101 over 100. So negative 101 over 100. Redistribute the 5 back through. You get 5 times p plus 9/10 squared minus 101 over 20. Again, I'm not using any decimals here. Then solve for p. Again, you got to become extremely comfortable with fractions through this whole process. So I'll add over the fraction. I get 5 times p plus 9/10 squared equals positive 101 over 20. I got to get rid of this 5. So it's being multiplied, and I could divide it, but I already have a fraction. So the equivalent to dividing the fraction would be multiplying by its reciprocal. If I multiply by 1/5, 5 times 1/5 is gone. I have p plus 9/10 squared equals, I think we're back to 101 over 100 again, because you just multiply straight across the fractions. So 101 over 100, which is going to work out really nicely for square rooting. So we have our quantity squared. So we're going to square root both sides, plus and minus, and we have p plus 9/10 equals the square root of 101 over 10. Because if I do 101 and 100 as separate square roots, I can actually square root 100 to be 10. 101 will not simplify anymore. Pretty sure it's prime. So then we have p plus 9/10 equals plus or minus the square root of 101 over 10. We'll subtract over the 9/10 and get negative 9/10 plus or minus the square root of 101 over 10. They do have a common denominator. If you would like to make that negative 9 plus or minus the square root of 101 all over 10, you can. They are the same thing. Notice that last form sort of looks like quadratic formula format, which again, you're also welcome to do if you would like to verify it. But this again is the process of being able to use completing the square to actually get your solution. And you're also welcome to go and do the zeros for this, so on the calculator. But graphically solving them, if you get the decimals for those, that ends up being, again, with the plus or minus the two answers. You end up, p is negative 1.904988. Again, it's a decimal approximation because these are square root answers. The values are irrational. They're decimals that have no pattern, that never end. So exact is the square root answer. The other decimals will just be approximations. The other one is a positive 0.10498,756. Again, those keep going in no particular pattern, but it's about negative 1.9 and then 0.1. But you can't approximate those unless the problem asks you to, and the exact answer would be the positive and negative of that square root quantity.